Okay, so this is the HL video for stereochemistry. I had a couple of requests for like formalized notes so that people could get a more concrete idea of what we were talking about rather than just the models. So here it is. So the very first thing is remember that stereochemistry is all about the three-dimensional arrangement of atoms in space. So this is different from an isomer, which is a structural difference along the carbon chain. Stereochemistry, these are going to have the same exact setup, except they're going to just be different in their orientation. So stereoisomers, these are molecules with the same connectivity, so I can trace it from carbon to carbon to carbon to carbon, or carbon to carbon to carbon to carbon, and nothing is different. But there's a different arrangement of the atoms in space, whereas this carbon is, both of the carbon groups are flipped up, or both of the carbon groups are opposite of each other. Remember that if they are on the same side, it is cis, and if they are on the opposite side of the double bond, it is going to be trans. Keep that in mind. We're going to come back to that over and over. These are called geometric isomers. For us, you can just call them typical isomers or stereoisomers. And then we're going to start to talk about this idea of diastereomers in a bit here. So keep that in mind as well. Alright, so we're going to talk about the different types of, the best way to put it is the omers, the stereoisomers, the enantiomers, and the diastereomers. So an enantiomer is a non-superimposable mirror image. This is what we were talking about with like the chiral carbon atom. And it is where I can take an atom that has 4 different bonds, carbon that has 4 different bonds, and I can rotate it in space so that they don't ever quite match up. It's just like your hands. They don't go over top of each other, but instead they are mirror images of each other. So these enantiomers are non-superimposable images. They do not match up perfectly. Just like your hands. These are said to be chiral. This is the idea of the chiral carbon atom. So I'll just draw an example. So if this has bromine, chlorine, CH3, and then let's have an OH group here. That is not going to be the same as if I have bromine, CH3, chlorine, and OH, because I can see that these two groups have switched locations. No matter how I turn one of them, if it's going to be clockwise or counterclockwise, they're never going to match, because in the example on the left, I have bromine is next to chlorine. The two halogens are near each other. But in this situation, bromine is opposite of chlorine, so they just are never going to match up perfectly. So then these are enantiomers. These are non-superimposable mirror images. And then also the idea is that this chiral characteristic, this would be a chiral carbon atom. So we'll go on to look at many more examples of this as we go on through this, the notes. Okay, so this is kind of a lot of text. You might want to read it. So molecules are not chiral if they contain a plane of symmetry. So if I can draw a line down the center or in any way, shape, or form so that I do have a sense of symmetry, then it is not chiral. Very important. Molecules that possess this mirror plane of symmetry, they are superimposable over each other, so I can put them on top of each other on their mirror image, so they are called achiral. A meaning without, chiral meaning chirality. So they're without chirality. So then this is just me hammering it home again. Supersymmetrical molecules are not chiral. The chirality center, or the chiral center, this is just talking about the carbon that's bonded to this thing. So this would not be chiral because I can draw, you can see here that I could impose these over each other. They match up pretty perfectly. The angles make it a little bit harder to see that, so I would just have to tilt tilted so they sit on their hydrogens. So the 3 hydrogens are pointed down, and then the 1 oxygen is pointed up, or what I would assume to be an oxygen in this case. Remember that because of this, they can be slid across each other and match perfectly. This is the only example of what could be deemed a chiral carbon, because it has 4 different constituents on it. So this chiral would be chiral, or we could call it asymmetric, or a stereogenic center. This is what IB uses, chiral. So just keep that in mind as we go along. So enantiomers are non-superimposable mirror image isomers. So I'll show you what I mean here with this example. So when we are talking about 2 carbons that have, or I guess we don't even need to limit it to a carbon, 2, what's the word I'm looking for here? 2 molecules that have a chiral carbon. So in this example, we have 1 chiral carbon in each of these. If we're talking about 2 molecules that have a chiral carbon and all of their constituents are the same, so I have methanes attached to methyl groups, I have a carboxylic acid group, I have a hydroxyl group, my alcohol, and then I also have a hydrogen as well. So they have the same constituents, they have the same branches, they have the same chain length, excuse me. They have the same functional groups, but their orientation in space is different. Because they don't match up, these 2 are enantiomers of each other. So when you're using the term enantiomer, you're talking about comparing 2 similar, but sterically speaking, so in terms of their orientation in space, they're different. So this is a word that is used to compare carbons with similar constituents. So keep that in mind as well. Down here, we can start to look for these planes of symmetry in an astructural carbon. So one of these is only going to be a good example. So right here, you can see this hexanal, cyclohexanal, has a line of symmetry right down the middle. I can put it right there, fold it over, and it's going to match up perfectly. What you should also see here is, in this example, there's not a carbon that has 4 different bonds. So this one has 3 hydrogens, this one has 2 hydrogens, so I could pretend like I was cutting it down there and my hydrogens would still match up. This one has a double bond, so it definitely cannot be chiral. A carbon needs to have only single bonds, 4 single bonds for it to be chiral. And then this is an oxygen. This last one on the right is an oxygen. Doesn't matter. Here, though, this guy has 4 different constituents. It's got a methyl group, it's got a hydrogen, it's got an alcohol, and then it's got a carboxylic acid. It is just an image of this atom up here. And lastly, over here, you can see this doesn't have a plane of symmetry. So I have that same cyclohexanal, but there is a methyl branch that wrecks that plane of symmetry. So these chiral carbons, these little spots where the carbons are, that's going to be the chiral center. It's going to be stereogenic or asymmetric. Any one of those terms will work, but you should be seeing IB use the term chiral. Chiral carbons, a chiral center. This is a chiral molecule, something along those lines. So here is the next little introduction to the vocabulary. So remember, enantiomers have chiral centers that have mirror images, but they are not superimposable. So if you have an enantiomer that has more than 1 chiral center, so if it's more than one chiral, then all chiral centers must have the opposite configuration. all of them need to not be able to match on each other. This is key because now we start to talk about diastereomers. In general, so right here, I'm just moving down to the next point. Enantiomers have basically the same exact physical properties, except some of them just rotate plain polarized light. We're going to get to that later on. Diastereomers have completely different physical properties. This happens with proteins and amino acids. There are two different ways we could orient an amino acid because there's two chiral carbons there. Your body is made up of only one way of orienting it. So every carbon is situated this way in space, and there's no variation from it at all. So your body does this. It uses this idea of diastereomers having different physical properties. It uses that to its advantage to help build up these proteins, these long chains of molecules that give you muscles, give you enzymes, give you all these wonderful things. This is just a general rule. IB's not going to ask you for this, but they might. So if you have a molecule with an n number of chiral centers, there are 2 to the nth power of stereoisomers possible. This is not including geometric isomers of double bonds. So for example, if I know that I have a molecule with, let's say, 6 chiral centers, and I wanted to know how many stereoisomers are possible. You would just do 2 to the 6th power. 2 times 2 is 4, times 2 is 8, times 2 is 16, 32, 64 different stereoisomers. 64 possibilities. I'm not going to ask you this on the test. IB might ask you this, but with a much smaller number, hoping that you could draw out all the different stereoisomers. You can use this rule and spit out the right answer too. Save you a lot of time. So now we're going to start to look at the idea of diastereomers and enantiomers. So this is just a pictorial demonstration in that I'm going to show you this so that you have an idea of what the difference is. So what we have here is 4 representations of the same atom. We have 2 chiral centers in each of these. So here's one chiral center and here's the other. And I kind of have them divided up like this, where if I took the one on the left here, so I'm going to label this one left, and the one on the right, that is supposed to be a G, I apologize, I can pretend like they're my hands. I can flip them over so that they match, but they are not, they're non-superimposable. So if I slide them over, they don't fit perfectly. They are mirror images of each other. If I put a mirror up in between them, I would get the other one. Same exact situation on the right here. So this time I'm going to actually, this is left, this is right, and I'm going to just put a mirror up. And you can kind of imagine that everything is flipped around and reversed. So if this one has bromine on top and hydrogen on the bottom, you're going to get the same top to bottom orientation, but it's just going to be on the opposite side of the molecule. The way we notate if it's which way, if it's left-handed or right-handed, is S and R. So this would be a left-handed molecule, or a left-handed chiral center, and this would be a right-handed. You are not expected to do this for IB. But I gave you the proper name so that you can see that I could end up with SR, but the mirror image, the enantiomer, is going to be RS. Same thing over here, back to our original example. This is where I'm looking. I have SS, so I have 2 left-handed chiral centers, and the other one I'm going to end up with 2 right-handed chiral centers. They are mirror images. I could compare any one of these to its non-enantiomer and it would be a diastereomer. So the two that I'm going to circle in purple, this guy, and I'll pick this one here. These are diastereomers of each other. They're not mirror images, but sterically speaking, they're different. They're oriented in space differently, but they're not mirror images of each other. That's what a diastereomer is. So you have an enantiomer, which is a perfect mirror image, like your two hands, and then you have a diastereomer, where you have two chiral centers, two chiral carbons, and they're different, but they're not totally different. One is the same, so I can see the first carbon has the first R orientation, and the next one is different. This one has a right-handed orientation, whereas the next one has the left-hand orientation. And then you can also notice this here. They match up perfectly on one half of the molecule, but differently on the other half. It's kind of like E and Z, but because it's a chiral center and not a double bond, it's not exactly the same. Similar, but different. This is more just examples. So what I'm seeing here is if I drew up a mirror, they match up perfectly with each other, so that if they are going to be mirror images, I can take this one and flip it over. And then the same thing over here with this one. They are mirror images of each other. But if I compare this one to the other one that is not an enantiomer, I can notice a difference. This orientation is the same, but my other orientation right here is not the same. They're different, but not totally different with two chiral centers. That's what a diastereomer is. Non-mirror images, but different in space, different sterically speaking. Diastereomers, and this is our formal definition, this also occurs when you have the cis, trans, or EZ formation. This is like the idea that you have two things that are different but not totally different. Most specifically with the EZ orientation. That EZ orientation is going to be considered a diastereomer 100% of the time. Okay, so this is going to be the last little bit. The idea of optical activity. So in enantiomers, they will have, they're going to be optically active, equal but opposite. Remember, enantiomers, these are our mirror images. These are perfect opposites of each other. So they work the same but opposite. We basically just send plain polarized light, and then in this is this green area, this is the sample tube, and we just measure how much it changes. If it changes more one way to another, we know a certain percentage of that compound. So if it's like, if the left-handed molecule rotates at 5 to the left, and the right-handed molecule rotates at 5 to the right, then when you run it through a sample, if it rotates 1 degree to the right, then you're able to do a quick math equation and spit out, okay, well, I have this much percentage of my right-handed molecule, and this much percentage of my left-handed molecule. What you guys need to know is the different parts of it. So the plane polarized light goes through a polarizer, it weeds out all the things that aren't in the same plane. Then it goes through the sample tube, and then you have an analyzer that measures that change of angle. So this measures the change of the angle, change of theta, change of alpha, if you want to follow that along too. Properties of enantiomers, this is really unimportant. You could stop watching here and you're not missing any content. In general, they have the same physical properties, but they just rotate plane polarized light, the same magnitude but opposite directions. Everything about them is the same except for the way they change light. This is, again, the idea of mirror images and then diastereomers. So you're more than welcome to look at this on your own time. This is a good one to notice. These are actually identical, because if I flip them over, they will match up. And this is just because now I have a plane of symmetry. I can take those two and fold them over that line, and then they're going to be identical. So we really only have one way of naming this, and they would be the same thing. But because of that, all three of these are still diastereomers, oh my goodness, diastereomers of each other. I need to stop talking about this. This is your isomerism notes in a nutshell. I'm not going to talk about this anymore. Read it, write it down, come with questions. Have a good rest of your break. Well, I guess it's not break for you guys. See you all soon.